Welcome to the first lecture on wave optics. Today, here's what we'll be looking at. First, we're looking at the wave nature of light. We've been thinking about light in terms of particles or rays. When we did the geometrical optics, we would trace a ray and follow it to its conclusion. So now we're backing up and we're looking at some phenomena having to do with light that indicates that it's a wave. If you look at Huygens principle, waves are every wave or every piece on a wave front generates a new wave front. And so you can see that he's got these little waves thrown, little spheres, basically, if you're looking in three-dimensional. And it turns out everything cancels out except for the piece that keeps going straight. All right, so that's really the view of wave propagation we're going to look at here. Now we have the index of diffraction, which is V equals C over N. And we have C equals lambda F, and since F doesn't change, we're going to define a wavelength in a material, lambda N, as lambda over N. Now, if we were talking about a door, right, we're shining light through a door, we expect that door to cast a fairly straight shadow, right? Shadows don't really, light doesn't typically bend around the corners or anything like that. It's pretty straightforward. Sound, on the other hand, does bend around the corners. And the real reason there's this difference is that if you take like a B4, right, it has a wavelength of 660 millimeters. So about 0.6 meters. That's comparable to the size of the door. But if you look at red light at 660 nanometers, that's 10 to the minus 6 smaller. So the door is enormous compared to light wavelength versus the sound wavelength. So what happens when you start making a slit or the doorway smaller and smaller and smaller? All right. So if light is in fact a wave, you expect to see interference patterns due to the fact that it's a wave. All right. You develop, and so Young did his double slit experiment where he put two slits in, he shone a light on it, and he looked to see what the pattern was over here. And the goal was to demonstrate that light was in fact a wave. Well, if you work through the mathematics of it, if light is a wave, then you expect to get constructive maxima at d sine theta equals m lambda. And you expect to get destructive minima at d sine theta equals m plus 1/2 lambda. And here m is just an integer. All right, just an integer. And why is that? Well, if we look in detail at what's going on right here, d sine theta is this little piece right there. That's d sine theta. And we're saying, so basically, when the shift between light coming from here and light coming from here is an integral number of wavelengths, then it's going to add constructively. And when the shift between them is half a wavelength, it's going to add destructively. It's exactly what we expect to happen with waves. So Young did his double slit experiment, and what he found was something that looked about like this, where you've got a bright central maxima and then you've got your other maxima off to the sides. It all worked out just as if light were a wave. It's what he expected. Okay. Now, because of the dependence on the wavelength, right? Once you start adding in more slits, what happens? Well, among other things, the peak from the double slit narrows as you add more slips, right? As you add more slits, that peak narrows. And because it narrows, because, red ends up here, right? And yellow ends up here, and blue ends up there. Because it narrows, you can actually begin to resolve the differences in where the different colors go. You can begin to pull apart the colors that are in the light coming through here. This makes this a diffraction grating. This is what we used when looking at the fluorescent lights one day when we saw the different lines that were in the fluorescent lights. It was a diffraction grating. And what we were looking at was this first order rainbow from the diffraction grating. It was set up so that you looked at that. So central peaks on the diffraction grating are still at d sine theta equals m lambda, right? That's where they are. Again, that dependence on lambda is what helps us separate out the colors. The other question is, could you get single slit diffraction? And the answer is yes, you do. And you get single slit diffraction for exactly the same thing. Light heading over here goes through different distances to get here, so you get constructive and destructive interference. So it turns out with single slit diffraction there is a destructive interference at d sine theta equals m lambda. Remember, over here it was a constructive interference at d sine theta equals m lambda. Here it's destructive, and the zero case is gone because you've got your peak at 0. All right? This actually happens coming through your doorway, but d is so big compared to lambda that the angular separation between the central peak and these minima is so tiny we just never notice. All right. This also led to what's called the Rayleigh criterion. And Rayleigh looked at these minima on either side and said, you know what? We can't resolve things until they separate it at least by, from here to here. Right? If we have a central peak here and we have a central peak at the minimum for that peak, then we'll be able to resolve them. If we don't, we're not going to be able to resolve them at all. So he worked out the math on that, and it turns out we're looking at an angle of about theta equals 1.22 lambda over d. And you can see examples over here of the same thing in different pictures with different d's, right? And you can and can't resolve to various extents depending on exactly what's going on. This is a limit on telescopes because it changes exactly how far apart objects have to be for a telescope to be able to resolve them. It's actually a limit on lasers as well. If you shine a laser at something, because of diffraction, it actually spreads out, right? Actually spreads out into a larger spot.